Okay, so in this video, we're going to look at affine transformations. They're really just a small extension of the transformations that you've already seen. So as a quick reminder, so far you have seen on this course two different types of transformations. You've seen the use of vectors to carry out translations. You'll have seen that way back when you were doing functions. So the vectors are of the form two numbers, let's call them E and F, in a vector, and they define the movement in the x and y direction. Okay, and then as you've just seen, we have transformation matrices that we use for linear transformations, and these are 2 by 2 matrices of the form A, B, C, D, where A, B, C, and D are just some numbers. Okay, so affine transformations just combine these two types of transformations so that we get a linear transformation and a translation, so that of the form we can say AX plus B, where A is some transformation matrix. This X is just the point that's being transformed. Remember, we think about transformations point by point. And B is your vector translation. Okay, so if we're thinking about what that looks like as a matrix, you'll have some transformation matrix, A, B, C, D, multiplied by your point, so some x, y coordinates, and then you're adding on some vector translation. Okay, and it works just like normal algebra. We do that multiplication, that vector multiplication first, and then we add on that translation. Why are these useful? They're useful if you have shapes that you want to resize and move and replicate a lot, particularly if we're creating things called fractals, which are sort of patterns and shapes that are self-similar. So look the same pattern at different scales. I was thinking, if you imagine a broccoli, if you zoom in on a broccoli, kind of looks the same as if you zoom out on a broccoli. They have the same pattern. Okay, so let's look at an example of one of these. So we're given points on a shape P, Q, R, S, and we're given those coordinates, and they're transformed onto, now remember, this P dash here just means the image of P, and then the image of Q, R dash the image of R, S dash the image of S, and we're applying a transformation, and this transformation is an affine transformation. We have some transformation matrix A, and we have some vector B, and X here is our point, XY coordinates. Okay, so part one, we are asked to find the coordinates of the image of P, Q, R, and S. Before we do that, I just want to have a quick think about what we expect from this. Looking at the transformation matrix here, we can see that it's got 2's on the diagonal, so there's probably going to be some enlargement involved. If you remember that the general format of an enlargement transformation vector will be K, K, 0, 0, so there's some enlargement, and there's probably going to be some reflection or rotation, because we can see, well, actually it'll be reflection, because here we've got positive and negative on this diagonal, but the same on this diagonal. And if you remember, if we have cos 2 theta, sine 2 theta, sine 2 theta minus cos 2 theta, that's our general reflection in the line y equals tan x. Now, I don't know exactly, because obviously when these are combined, as you'll have seen, you can combine two transition matrices by matrix multiplication, so it's not always so straightforward to see. But we're expecting something like that when we finally get the image and draw it out, just to check. So that's useful just to visualize what you might be expecting, but it's not necessary to carry out question one. So question one wants us to find the coordinates. So all I'm going to do is I'm going to take this formula that they've given us for the affine transformation and substitute in each of the coordinates one after the other. So the image of P is just this matrix multiplied by the point P, which is minus 8, 2, and plus 20, 15. You can type that straight into your calculator. and that will give you the point 36, 19. I do the same thing for Q, so again I'm doing -2, 0, 0, 2 multiplied by 4 minus 3. When you're doing affine transformations on multiple points, it's often really useful on your calculator if you've saved that matrix A and saved that vector B, so you don't have to keep typing them in, so store them on your calculator. That gives you the point 12, 9. I'm not going to write out all of the rest, but if you do the calculations, you'll get that the image of R is at 8, 19, again just substituting it into that transformation formula at the top, and the image of S is at 12, 29. Okay, and that's part 1 done. I would sketch it out, and I will do that in a moment, but I'm going to look at part 2 first. So, question 2. The coordinates of the point whose image is 10, 14. So previously I had the original points and I was finding their image. Now I have the image and I want to find the original point. Okay, well, let's write out what we know, just like we would do with algebra. So we have this general formula. So the image of some point x is this transformation matrix multiplied by some original point x plus 20, 15. And we know that the coordinates of the image is 10, 14. So I can substitute that in here. And everything else stays the same. Okay, and now I need to think, just like with algebra, what am I interested in? Well, I'm interested in this x. This is a vector, remember, it's going to be the coordinates of 1 point, sorry. Well, how can I get x on its own, just like I would with algebra? Well, first of all, let's take away this vector 2015 from both sides. So here that's going to give me -10, -1. And on the right-hand side, I'm left with the same. And that's because I know that I can just do matrix or vector addition and subtraction, just like I would do with normal algebra, subtracting the x components and the y components separately. Okay, but now I have the problem. I want to get x on its own, and it's multiplied by this matrix. Now, remember, when I'm trying to undo multiplication, in normal algebra with just numbers, I would divide, but I can't divide by this matrix. I need to use what we've already seen, which is the multiplicative inverse. So of this matrix A is just going to be noted as A to the -1. So I'm going to use that. I'm going to multiply both sides. I have to do the same thing by both sides. Multiply by the multiplicative inverse. That's because if I do the inverse of A times A, I'm left with the identity matrix, which is the same as effectively multiplying by 1 in the sense of real numbers. So the identity matrix times x will just be x. Okay, great. So I can write that out. Both sides I'm multiplying by the multiplicative inverse. Just put that in a different colour to make it super clear. And what will that do? Well, here we've said that's just the identity matrix. The identity matrix times x is just x. So that will leave me with x is equal to, and I just need to, on my calculator, multiply the left-hand side together, and that will just give me 5 and minus 0.5. Do be careful, the order matters. With matrix multiplication, remember it's not commutative, so this always needs to be first on both sides. Okay, and those are my coordinates of the point x. Officially, if it's asked for coordinates, I should write 5, -0.5 as my coordinates. Okay, and I said we just wanted to check what that looks like. We're not asked to do it, but just as a sense check, what does that look like on a set of axes? So Here I have included, just sketched down at the bottom, the original 4 points. And now I want to sketch in the points that I worked out in part 1. So 36, 19 is my first point here. That is the image of P. Then I've got 12, 9. So 12, 9 is going to be here. So that's the image of Q. Beg your pardon, P should be slightly further up. I've just misread that scale. Okay, R dash is at 8:19, so that's going to be 8:19. And S dash is at 12:29. Okay, so you can see, if you imagine both of these sort of forming a shape, if you imagine connecting these up, we can see that it's a sort of kite shape. And if I do the same thing with the image, well, we can see what's happened to the shape. It's obviously been enlarged by a factor of 2. That makes sense. That's what we were expecting. And it seems to have also been reflected in the vertical line and then translated, probably reflected in the y-axis and then translated. So that's what we expect. That's good. We can also check our answer to part 2. Part 2 said the coordinates of the point whose image is 1014. Well, let's look at this point 1014. That's this point here. And it's on that line of the shape in between the image of Q and the image of R. Let's check if we look on the original shape in between Q and R. That's somewhere here. And we said we expected that to be at 5 minus 0.5. Yes, that looks correct based on what we've got. So it's a good sense check. Okay, I suggest you practice some questions on affine transformations.